last one near where I live. Couldn't compete. There is a new Westinghouse model, an AP1000. 4 are being built in the US, 4 are being built in China right today, and some in other places. If I go through the normal math about how much this is going to cost, I come up with about 8 cents a kilowatt hour for electricity from the new fangled power plant. That's not going to be quite good enough. It's not cheaper than coal, and it's not cheaper than natural gas. So we can't expect the world to give up coal for these kinds of reactors. So we need a new approach. In the space program, we rejuvenated that program by going to privatization. The company SpaceX looked at the situation with NASA and said that the space shuttle was a complex instrument using 1970s technology, and it had not been upgraded. So Elon Musk, that entrepreneur, said, okay, let's form a company, let's be innovative. They designed an entirely new rocket engine. They put together small teams with low overheads to fabricate and design new kinds of rockets. And 6 years after founding the company, they had their first flight. Their first success was this product for $400 million, successful, where NASA had estimated as much as 10 times that cost. So there is an opportunity for cost innovation in space and in nuclear power. And I say that the liquid fuel form of a nuclear power plant can provide that kind of cost innovation, as was done at Oak Ridge. Back to solid fuels just for a minute to compare the two. Here's what goes into a nuclear power plant on the left. It's uranium, but it's been enriched to about 3.5% of that isotope called 235, which is the fissile one you want, from less than 1% in normal mined uranium. Coming out the other side, you get the fission products from splitting those atoms in half, the barium, krypton, cesium, that sort of thing. You get about 1% plutonium, some uranium is never burned, and then lots of 238 still available. That plutonium, by the way, has been being burned up inside today's nuclear power plants too. It's a perfectly good fuel, and about 1/3 of the power of the power plant comes from the uranium that was created by bombarding the uranium-238 with neutrons. But meanwhile, in the solid fuel plant, all that's happening inside this sort of ceramic uranium oxide pellet that is stuffed into a zirconium fuel rod that protects the fuel from the water in the surrounding the fuel rods. We have to take those fuel rods out before we get well into the consumption of the potential energy there, because we're afraid they might crack. In a liquid fuel reactor, you don't have that sort of problem. You can leave the fuel in the reactor for quite a long time. And on the bottom, we're trying to show those heavy metals like uranium and neptunium, plutonium, and so on. If they absorb neutrons, they just stay in the fuel mix and are eventually fissioned into the fission products that a normal power plant generates. There's 3 kinds of fissionable power sources you can use in a nuclear power plant: the plutonium we spoke of, the uranium-235, and also an isotope that's not naturally available anymore, uranium-233, that we can actually create. Here's the example of creation of plutonium in a power plant. Neutron absorption, in this example here, where the rows represent the atomic weight of the atom and the columns represent the number of protons in it. That neutron absorption creates a kind of uranium that's not stable and decays in a few days to plutonium, which is a fissile material that burned in the power generation. Same thing with thorium. Thorium absorbs a neutron, decays in a few days to uranium-233, which is a useful fissionable power source. So that's the idea of a thorium reactor. It literally creates its uranium on the fly from the thorium. Weinberg invented another kind of reactor that used liquid fuels. In this example, it wasn't thorium yet. It was still a uranium reactor, but what they did was to melt a salt of lithium fluoride and beryllium fluoride, and dissolve in that salt the uranium fluorides to be a carrier for the fuel, and also to transfer the heat. And that was the first such reactor back in 1954. It did work. Then he had a vision of using it with thorium, but wasn't quite ready yet. And they did one more test reactor in the 1960s to do better research on the technology. So that was successful as well at Oak Ridge National Labs in the US. Now, the way these reactors work is in the orange core there, we have a normal nuclear power plant fissioning reaction where the U-233 or 235 atoms would fission, and neutrons would then fission others of them. But extra neutrons would go into a blanket around it with thorium, and those thorium atoms, when they absorb neutrons, would decay to U-233, and there was a mechanism to basically chemically separate them out and take that newly created U-233 fuel and put it back in. That was the first concept of that liquid fluoride thorium reactor. Same thing on the way out, we would take that fuel, use the hot fuel to go through a heat exchanger and eventually run a turbine generator, and also separate the waste products from but waste in the sense of the fission products, the barium, the krypton, the xenon, the cesium, and so on, take them out. That was his vision. He felt that humankind's whole future depended upon this really inexhaustible energy source. So he was consumed with trying to get this product completed. He never succeeded. There's another variation on that that's more likely to happen in the very short term, and that's a single fluid reactor, much simpler, called the denatured molten salt reactor that many of us are working on. And in this kind of a reactor, the uranium that comes in is mixed U-235 and 238, like in a typical light water reactor, but in a form that dissolves in the salt. Also, another input is thorium in the same way. So there's only actually one big vat of liquid that generates heat that is eventually converted to electricity. What China is doing in its first molten salt reactor is the same thing that MIT and UC Berkeley have done research in, but not executed yet, and that is a so-called pebble bed reactor that's cooled with the molten salt. So instead of dissolving the fuel in the salt, the fuel is going to be kept in those pebbles that are about the size of billiard balls, and inside them are thousands of grains of sand, where that sand is really uranium oxide, covered with 3 ceramic layers to contain all the fission products within those billiard balls. So this is a near-term objective in China, which hopes to have this up and running in 2017. When I do the costing, I find that I believe we can do this electricity from a thorium-based liquid fluoride reactor at about 3 cents a kilowatt hour, and have one person who has done a rather complete design over the last few years who has costed it and comes up with the same number. Why? Why is it cheaper? Well, number one, the molten fluoride salt is not very expensive. So the fuel containment mechanism isn't very expensive. The heat transfer works really well, partly because we can run that reactor at a very high temperature and get the energy out of it quickly. The other nice thing is it runs at atmospheric pressure, so there doesn't need to be a lot of reinforcement. A normal light water reactor, like at Fukushima, for example, had over 100 atmospheres of pressure, and so that required that the big vessels be strong to contain the pressures. Now, the safety is more intrinsic and dependent upon just the physics in this sort of reactor. The reactivity is stable. That is, if the reactor gets too hot, the fission rate goes down. If the reactor gets too cold, the fission rate goes up. It's just natural from the physics. Doesn't require any control rods or mechanical things to happen. The other thing in this reactor at the top of the picture, in the top vat, is where the reaction takes place, and at the bottom in the picture is a so-called drain tank or dump tank. Keeping that hot liquid in the operating reactor is done by having a plug of that kind of salt, which is in a solid form, in a tube near the bottom of that vat, so that if the reactor were to overheat, all that salt would melt the plug and it would just sort of drain naturally into the drain tank, again, without any physical controls or operator actions. So it's another example of intrinsic safety rather than engineered safety systems. Because it's at atmospheric pressure, if there were some sort of an accident, there wouldn't be a force to propel radioactive materials into the environment. And if there were just a rupture, the salt would, it would be a mess, but it would leak out onto the floor, contaminating the building, but it would lie there and slowly solidify. Another example is the fact that this is a very small reactor. It was designed to have low mass. The original motivation for the design was one small enough to be an airplane engine. Compare that to what's going on at the AP1000 in China. Just the roof of the containment building is a big lift, 780 tons. Some advantages of that liquid fluoride thorium reactor are the high temperature. The higher the temperature of the reactor, the more efficiently you can extract the energy from the heat. And this example is a technology that South Africa has tried, but hasn't really worked on a commercial scale quite yet. It's a so-called closed cycle, Brayton cycle with helium to convert the heat into mechanical energy to run the generator. Again, the high temperature helps. The higher the temperature, the more efficient the conversion, the less waste heat we have to reject into the environment, the less water cooling, and the less water consumption by that kind of reactor. There's also an open air version of this that works reasonably well. There's some new technologies coming down the stream. These pictures are more or less to scale. There's a traditional steam generator in blue at the top. The helium turbine that was going to be used in South Africa, and the new kid on the block, the supercritical CO2 turbine being developed at Sandia and I think at MIT, much smaller, but not at commercial scale yet. There's lots of thorium. One spot in the US has that much thorium. There's plenty. We only need about a ton a year per reactor. There's particularly a lot of thorium in the beach sands in India, Brazil, Turkey. There's actually about 5,000 tons in Taiwan on the beaches on the southwest shore. And it takes about a ton to run a city for a year. again, compared to the light water reactor, we don't need as much, we don't need to mine as much of the metal to start with. And the other thing is that in the sort of the best example of the lifter with two fluids, we can have a very, very small amount of waste radioactive material at the end. In fact, after 300 or 400 years, the radioactivity of the waste products of these kind of reactors is actually less than that radioactivity of the natural uranium ore that was mined in order to create that fuel. Another thing we can do with smaller reactors is assemble them in factories, in modules. And I give this example of Boeing aircraft that can make an airplane every day. Plus we have Airbus and others who do that. They have the same sort of problems about life safety, documentation, strength of materials, temperature. It's very possible to develop assembly lines to make these kinds of reactors. And the more we do that, the lower the costs can drop. This is the classic learning curve for manufacturing. Once we get into repetitive manufacturing, we can begin to get the benefits of the learning curve and drop costs. This is a way to get energy cheaper than coal. Suppose we actually did say, okay, now